All right, everybody, in this video we're going to take a look at the conjugate root theorems. So this video will serve as an introduction to those theorems and as an example of how you might complete problems like the one that's on the screen right now. We'll use these problems to help us understand what the conjugate root theorems say. So let's dive in right away. The problems on the screen say that we should write a polynomial function of least degree that has rational coefficients, a leading coefficient of 1, and the given zeros. Seems like a lot of constraints, but the one thing that is going to be very important for us is a pair of theorems that we will call the conjugate root theorems. For example, we could treat example A, and I will need to space these out a little bit. These problems are going to take some room. So we'll manage that as we need to. But if I treat example A like any of the other find a polynomial function, that would mean we would write out a bunch of linear factors, a bunch of parentheses, that would include an x minus that 0. So this 1 goes into a polynomial that has x minus 1. We can do the same thing with the next of the zeros. But first, let's actually take a look at those theorems. All right, here they are. They are collectively called the conjugate root theorems. And we have one called the irrational conjugates theorem and one called the complex conjugates theorem. And what they say is if you ever have a polynomial that has one of its roots or one of its zeros as a binomial involving a root, then also the conjugate of that is also going to be a root. And I guess I'm overgeneralizing a little bit. We can certainly have polynomials that have one but not the other, but the trick is they will not have a specific type of coefficient. This one it actually will have rational coefficients. So we have these roots in our answers, but we don't have any in the polynomial.
Our polynomial is just going to be, something x power plus whole numbers or integers or rational numbers, maybe some fractions, and that's it.
And then it works the exact same way for the complex conjugates. If we have a 0 or a root with an I in it, then its conjugate, same two terms, switch the sign in the middle, is also going to be a root. And just like we create rational coefficients, this one's going to create for us real coefficients. What it guarantees is that if we were to simply put x minus this 3 minus root 2, when I FOIL this out, I would get a polynomial that still has a root in it somewhere. But if I specifically want one with rational coefficients, I have to also say that not only is 3 minus root 2 a root, so is 3 plus root 2. Okay, and again, same two terms, I'm just switching the sign in the middle, which is going to give me another parenthesis, and that one will be x minus 3 plus root 2. And what the theorem says, before we actually dive into expanding this, what the theorem says is when I expand it, when I multiply it all out, the answer is going to be x cubed something something something, but no more roots. And that's what we want. That's how we meet that first condition of rational coefficients. Okay, so it'll be rational coefficients. They also have least degree. That just means we're not like throwing in an extra x factor at the front. I don't think you would want to do that anyway, but we could pump up the degree if we needed to. A leading coefficient of 1, that's one of the criteria. That means we're not going to toss a 3 out front or anything like that. And of course the given zeros. So what are we doing here? We're determining the extra 0 that we needed, the 3x plus 2, using this new conjugate root theorem. before we cut and try to finish example A, this will work like we already said with something like example B. Just give me a little bit of room. We'll move it down here. If I wanted to create this one and we want to have those rational coefficients and all that stuff, we would not only have the root 4 plus I, we'd also have 4 minus I. Again, the conjugate of the given complex root. And that means when we create our parentheses, we're going to have 3 of them. And the first one will be from the negative 6, x minus a negative 6, or x plus 6. They'll all actually start with x minus. 4 plus I is going to be one of them. I put it in parentheses because we're subtracting the whole thing. We're going to need to distribute that minus. Same over here. 4 minus I in parentheses. And example C might look like it doesn't fit the bill because this I root 3 is not a binomial. This one's actually going to end up giving us an easier problem to work with, even though it looks a little bit unusual. Let's go way down on this one. I think you're probably guessing that it's going to be x minus 4 for our first parentheses. When we try to write our other two, we're going to keep in mind that I root 3 is a lot like a complex number with the first or the real term being 0. So the real part's 0 plus I root 3. Well, what's the conjugate of that? It's going to be 0 minus I root 3, or just negative I root 3. So if you have one of these that just has a rational term or just has an imaginary term, or like this one has both imaginary and rational, we should be able to kind of extend this theorem a little bit and say it's just going to be the opposite. But that's only for when we have one term. Conjugate is a term that would apply to all circumstances here. So to round it out, we're going to say the second and third parentheses are going to be x minus, and for the first one, it'll be x minus I root 3. For the last one, from the negative I root 3, it'll be x minus a negative, or x plus I root 3. And you might be able to guess that this last one is going to go a lot easier for us because we don't have any trinomials to expand. So let's actually finish these. We'll start them over, but let's finish them. Let's expand them all the way and see where that gets us. All right, we just had our crash course in what the conjugate root theorems say, and now we're actually going to answer the question that we're being asked. We're saying write a polynomial function of least degree that has rational coefficients, a leading coefficient of 1, and the given zeros. Very daunting when you read it, but now we have the knowledge to move forward. To write a polynomial function with those degrees, and to make it a function, we could put in f of x. That's not really the important part right now. But the important part is that its factors, or its factored form, is going to include, of course, an x minus the first root of 1. It's going to include a x minus 3 minus root 2 also given to us. And then if we really want those rational coefficients, we use the conjugate root theorem and say we also have a 3 plus root 2, which again is the conjugate of the yellow one. And that one's going to form our third parentheses, x minus parentheses 3 plus root 2. And just this much, we can sort of clean up a little bit. I will drop, or I'll stop copying the f of x part until the very end. But we can simplify that minus parenthesis in these, so distribute a minus to both of those terms. You get negative 3 plus root 2. And it looks a little bit better already. We'll do the same thing in orange. X minus 3 minus root 2. And then we know that we could multiply any of those parentheses together. We have commutative, we have associative properties. So I could multiply like green times orange if I wanted, or I could multiply yellow times orange, or yellow times green. But maybe it's a spoiler, maybe it's just a hint or a recommendation. because yellow and orange are conjugates, or because these numbers are conjugates, I'm going to predict, and I'm going to go ahead and spoil it, when you multiply yellow and orange first, that will completely erase all your roots. So if you want to pick the easiest way to do it, I know it's like sort of counterintuitive that the two biggest polynomials, the two trinomials, should be multiplied together first. When we do that, we will not get any more irrational numbers. We will not get any more roots. So that's what I'm going to do. I'm going to sort of save this x plus 1 for later and multiply the yellow and the orange parentheses. And when I do this, because we have three terms in each, I try to do it as organized as I can be. So I'm going to first multiply x times all three of these terms. And when I do that, I will get x times, well, we'll go one at a time. I'm going to get x times x is x squared. X times negative 3, negative 3x. And x times negative square root of 2 is negative x root 2. And so far, it's not too bad. I'm going to do the same thing with the negative 3. Negative 3 times x is going to be negative 3x. And what I'll do, we've seen this technique before, rather than write negative 3x over here and just continue moving to the left, I'm actually going to make a column of like terms. So continuing on, negative 3 times negative 3 is going to be a negative 9. I'll put it in a new column because I don't have any other constants yet. And then negative 3 times negative root 2 will be positive 3 root 2. Negative times negative makes positive, which means also that my 9 should probably have been positive in the first place. And then lastly, we do have a positive root 2 that we need to multiply. So positive root 2 times x. Now how about this? That's going to go in the x root 2 column. They end up being not only like terms, but like terms that will be opposites. They'll cancel each other out. Positive root 2 times negative 3 gives me negative 3 root 2, which I'll put in that column. And then positive root 2 times negative root 2 gives me negative root 4. And now I'm sort of done with that step. I just need to put all these terms together. So if I do that, the x squared is going to be fine. I have a negative 3x and another negative 3x is negative 6x. These are both positive and negative the same thing. Actually, so are these way over here. They're going to be gone. And then, pretty importantly, this negative root 4 is the same as minus 2. Square root of 4 is 2, right? So I'm going to scratch that out and move that over here, minus 2, to give us a plus 7. And it's a little bit of organizing, but it's not like particularly difficult. We'll have to keep ourselves focused. We'll have to keep organized. But we took two trinomials and ended up with a single trinomial, which is great. That's a good rate on return there. We're not done though. We were supposed to bring down this x minus 1. Now it's just multiplying this binomial times a trinomial. So doing that, let's see, x times all that stuff will be x cubed minus 6x squared plus 7x. And then negative 1 will give me minus x squared. You could also put these into columns. I'm going to leave it this way for now. Negative x squared plus 6x minus 7. And then just one step later, we can come up with an answer by combining like terms. So, my polynomial function, that has a leading coefficient of 1, which it does. All the coefficients are rational. There's no roots left over. Lowest degree, I can't get the degree any lower, is here. And it has the roots that were given in the problem. Okay. For a first example, hopefully this one worked out well. We'll do another one. We'll actually do one with a complex number so that you can see how it's going to be the same. But if any part of this didn't make sense, especially like all that stuff that's going on in here, you can like obviously rewind and take another look at that. Make sure you understand where all the terms are coming from, how they're disappearing, and this should happen for just about all the problems that are like this. If you set it up correctly, then the work should kind of all shake out the same way. Okay, I'm going to load up the next problem and we'll get started on that. All right, for our second example, we see that the changes that have happened, we now no longer have roots, we don't have irrational numbers. We have i's, which make complex numbers. We want the same thing. We want a polynomial function, least degree, rational coefficients, leading coefficient 1, and the given zeros. And the setup is going to start out the same. We're going to have a function. The x minus 6 as a 0 or as a root gives us an x minus a negative 6 as one of our parentheses. The 4 plus I is going to give us 1, 2. But if we just multiplied by, x minus 4 plus I like that, then we're going to end up with i's in our problem. And we use one of the conjugate root theorems, the complex conjugate theorem, that says if we take that 4 plus I and find its conjugate and add that to the mix, the i's will go away. We'll get real coefficients. And for the purposes of this problem, they will also be rational because we don't have any roots, right? So I'm also going to add x minus the 4 minus I we just came up with. I'm going to follow most of the same step. I'll speed up parts of the video to keep it a little bit shorter. And the first step is to clean up all those parentheses. All right, so that step should look familiar. And just like before, you are allowed to multiply green by orange or green by yellow. The best way, the way that we are going to make sure that we don't have tons and tons of terms and that our i's disappear quickly, is to multiply the two parentheses involving those complex conjugates. So I'm going to multiply yellow and orange together. I'm going to try to stick to the same organization that I did last time, and that means I'm going to use some circles and underlines to keep me focused on what terms, and I'm also going to arrange the product into columns of like terms. So that'll look like this. Okay, and here we are. If you're not sure where some of those terms came from, just kind of rewind and watch through that part again. Hopefully you got the same terms that I did. And what we're kind of expecting is that the I terms are going to go away in some way. They're either going to cancel out or simplify, just like the roots did in the last example. So let's first not forget that there is an x plus 6 that we need to bring down. And that's going to get multiplied by whatever we get from adding all these terms together. That's going to include an x squared from right here. It's going to include a minus 8x from right there. And look at what goes away. The ix and negative ix are opposites and they go away. The negative 4i and positive 4i go away. And then I guess also very importantly, negative I squared, because I squared is negative 1, is negative 1 or plus 1. So whether you look at the 16 and the plus 1 and add them together, or I actually sometimes put them in the same column and just kind of cross this out, that gives us a plus 17. And now our last step is just to multiply the the green binomial and the gray trinomial together, which you can do in the columns the same way I did this one. But because it's just a binomial and a trinomial, sometimes, or usually, I write it out just as one line. So, okay, and then because 6 times 17 is 102, we end up with all that. And then just combining like terms, I'm going to end up with an x cubed minus x squared, 7 minus 8 is going to be -1 x, and 2. And now that it is completely simplified, we can say, big picture, that we took those given zeros, used the complex conjugate theorem, wrote out our parentheses, multiplied strategically and organized, and ended up with a polynomial that meets all the criteria. Least degree, rational coefficients, leading coefficient 1, and the given zeros. So hopefully you're looking at this problem and saying, yeah, there's a lot of writing involved, and it looks like there's a lot going on, but all the steps are certainly manageable. And especially the most challenging part, the step where we have all the i's canceling out, that's the most tedious. But I wouldn't say difficult. I would say tedious or cumbersome. But just about in every problem, it should work out the same way. So let me set up one more of these. Our last example, it's actually going to be a shorter one. I'll do the same thing. I'll try to skip through some of the more monotonous parts. But we'll see one more type of problem. We'll talk about how they could get more difficult and where we're headed from here. Okay, so looking at now our example 3, in some ways it looks easier because we don't have binomials, but then it might look confusing because how do we handle it when it's not a binomial? It also might look confusing because we have both a root and an I. But we can handle them in the same way, and it's going to be okay, right? Process is going to start the same way. We do want this to be a function, so y equals or f of x equals. The constant is going to be an x minus that 0. And then, you know, I think it's pretty clear if you multiplied by x minus I root 3, there's going to be not only an I, but a root in our answer. So we want to obviously use one of these theorems so that we don't have i's or don't have roots. And what I need you to understand is I root 3 is a complex number. The real part is just 0. So it's kind of like 0 plus I root 3. And if I were to create the conjugate of that, it would be 0 minus I root 3, which is the same as negative I root 3. Okay, so when you only have one term, it's kind of like the opposite. That being said, I hope you understand why. And that means that we can just do x minus a negative I root 3 for our last parentheses. From here, same as before, multiplying yellow and orange is going to make sure those i's and those roots all cancel out. Those, in fact, are conjugates. Let's actually dive into that one. So we're not going to need as much work here because they're not trinomials. And because not only are these two numbers, not only are these two numbers conjugates, but these two are also conjugates because they are two terms, like two binomials multiplied together, same term, different sign in the middle. So what we should get if we multiply them together is the square of the first thing, or x squared, and then the square of the second thing minus the square of the second thing. So I squared is I squared. Root 3 squared is like root 9. That becomes a negative 1. That one becomes a 3. Negative 1 times 3, of course, is negative 3, so it'll be minus a negative 3. Or plus 3. Maybe I need to write that out. Minus a negative 3, which in the next step is going to be x squared plus 3. And now it's just a matter of multiplying together x minus 4 and x squared plus 3. And you'll have to forgive me if I went a little bit out of order. Maybe if you were multiplying using the same strategy, you would have gotten the 3x as the second term and the negative 4x squared as the third. I went ahead and switched those because we would probably like to put this in standard form. But you can see now how sometimes a challenging looking problem, because it's got all that stuff in it, and because it's not in the usual form, might actually be an easier problem to solve. Okay, one more quick setup. I want to talk about how these can get more difficult and where we're headed. Be right back after the switch. All right, so how could these style problems get tougher? Obviously, more is tougher, right? There's more to manage. So looking at something like let's call it example A over here. If you have a 0 as a root, you don't need to put x plus 0. You can just make that a root of x. I'm sorry. If the root is 0, you can make the polynomial just plain old x. They can be more difficult, like in this second one, B, if there are multiples that you have to use the conjugate root theorem on. So I'm going to have to make this one not only into a 1 plus I, but also a 1 minus I, and then also this one. This is 2 minus I, and then a 2 plus I. Sort of the trick to that one. They can be challenging, like example C, if the first term is negative. When you make the conjugate, you only change the sign in the middle. So it's not like a plus 2 anything. It's still a negative 2 minus root 8, which it's really strange that root 8 is there. I would think you would simplify that to root 2, but maybe that's part of the problem. And then lastly, you could have something like the last one, like example D, where you just have bigger numbers, also two conjugates, and also a mix of both irrational and complex numbers. None of that is more difficult, just more tedious, like we had talked about. And where are we headed? Like, is this the only type of problem that we're going to see? No. In fact, this is certainly one of them that we will see moving forward, but we can also use this technique to solve. Again, we kind of have to have a hint at this point, but if we know that we have one complex number as a solution or one irrational number as a solution, we should automatically get a bonus. So the next video that I record will be, how do we do a problem like this? How do we solve an x to the fourth that can't be factored if we know one of the solutions happens to be complex or irrational? So with that, thanks for hanging in there on this long video, if you made it this far. And if you have questions, as always, direct them my way, and I'll see you guys in class.